Presentation wise, oh, you're all set.
Is that all set? Okay,
Yeah.
great. Hi, everybody. So I can see some of your faces, but not all of them. Please don't make any faces during during the talk that I need to see. As Chen said, I'm also the director for the Center for Teaching Excellence, and so I've been doing a lot of faculty development during the pandemic, not just high school teacher professional development, and I don't know, maybe that explains why so much caffeine is needed, but it's really great to see you here. And I hope that we can learn together and that some of the pieces of this work resonate with you and support the work that you do. And I'm excited to talk more about you and what you do and learn from that. What I'm going to talk today about is a project called VisChem, and the focus of the project is trying to move from description to explanation within high school chemistry classrooms through professional development on molecular visualization. So I'll be talking about the professional development as well as some of the research that we've started here. Okay. The VisChem professional development and research team includes me, of course, but then also some really important people. Dr. Roy Tasker from Western Sydney, and Dr. Roy Tasker is the VisChem creator. He created the animations as well as the VisChem approach, and I'm excited to be working with Roy, an old friend. And also, Amelia Camus has just joined our team. She's an undergraduate student that's been supporting a lot of our inter-rater agreement for coding. But the heavy hitters that I want to showcase today are Dr. Matt Wu, who is a postdoc in the Yezierski Research Group, and Kat Magnon, who is a doctoral student. And they've done all this significant work today, so we want to give a shout out to them, as well as the National Science Foundation for supporting this work. And you can learn more about the VisChem project at vischem.org. All right, so where we started was we looked at that chemistry teaching in the high school classroom and professional development for high school chemistry is quite misaligned on a national basis with the next generation science standards. And it turns out that conceptual understanding in chemistry is really at the heart of NGSS. And we can see that when we look more closely at the science and engineering practices, specifically developing and using models and constructing explanations. If we look at the content, the disciplinary core ideas that are listed here are the three that significantly overlap the learning outcomes in a high school chemistry class. And so this misalignment with NGSS, is problematic. Um, and it's really problematic because the NGSS has a great deal of conceptual rigor. And so why is it like, why is there this lack of alignment? And we thought about that on our team, and it really comes down to two pieces, and that is that the nature of disciplinary knowledge in chemistry kind of creates this misalignment. I'll tell you a little bit more about that. And then also, chemistry's been traditionally taught in ways that don't align with how people naturally learn, and specifically it's not taught how people naturally learn chemistry. So reform is needed. And so when we take a look at reforming the chemistry, kind of thinking about the chemistry knowledge and then thinking about pedagogy, I'm going to kind of take you through a little progression of ideas. I like to call this the good news, bad news setup for the project. So I guess we'll start with the real news. And the idea is, what makes chemistry so difficult? And I think it's because chemistry, and what we know from the research, is that chemistry phenomena at the explanatory level, at the level of atoms and ions and molecules, that's an invisible level. So, we can experience some things in physics, for example, but, forces and things, but we can't really experience the phenomena that is important in chemistry. And so experts use a lot of symbolism, and when you understand the symbols, they work great, but they can be very misleading to a novice. The language is quite abstract and difficult to understand, and we go a little bit further and we generate a lot of metaphors and analogies to try to make things more concrete, but unfortunately it kind of leads us further and further away from the actual level of the phenomena. So three-level thinking is needed, which was popularized by Alex Johnstone, with the idea that when you have chemistry expertise, you can think about it on a macroscopic, particulate, or symbolic level, and that you can easily switch between those levels. But we see in high school chemistry teaching and learning that there's an overemphasis on the macroscopic level, that is like what the students do with labs and demos and things, and then the symbolic level. And because of that, there tends to be a significant focus on description, and because the explanatory level is the particulate one. Um, so that's kind of the bad news. But the good news is we know that particle visualization can actually build conceptual understanding. And we've learned from Jones and Kozma, Russell, Steiff, and others that we can bridge the invisible and the observable with molecular level visualizations. And there's been good outcomes from a number of projects that have been implemented in small kind of test sites around the country. And those relate to the use of animations and simulations. So that's a good thing. But when we look at visualization as a means for learning chemistry, it turns out that it has a very high cognitive burden. And we've learned that it's complex, right? You've got all kinds, these systems, have a lot of things going on and a lot of different things affecting them and happening. And you add to this switching between the symbolic and the particulate and the macroscopic level. And so the moving among levels of chemistry knowledge actually ramps up the cognitive load. And so one solution that some researchers have generated, which has been promising, is this idea of simultaneous frames. So, a student might be looking at a demonstration of a macroscopic, level of phenomena, and maybe a symbolic representation of that chemical reaction, or maybe an animation of that chemical reaction going on. So that has shown to have promise. However, that split attention actually increases the cognitive load. So it's almost like visualization is a good thing, but how we do it is really important, because if we implement it in a way that ramps up the cognitive load, then we're not likely to get students headed towards conceptual understanding. This challenge, I think, is compounded by the uptake of visualization in high school chemistry has been limited. That is to say that if we look across the country and we look at works like from Sean Smith and Eric Banalauer from Horizon, who do these large national studies on high school chemistry teaching, they see some things that the reforms are really not there. There's not a lot of explanation and conceptual understanding being evidenced. There's a lot of time spent on algorithmic calculations rather than immersive kinds of activities that would likely support student learning. And the other thing that we're learning, and this comes from some earlier work from McRobbie and Tobin, is this idea that the preparation ethic is really strong in high school chemistry. That is, a high school chemistry teacher views their role as preparing a student for college chemistry. And so I'll just editorialize a little bit because I've got you captive on Zoom, but this idea that we need to prepare students for really bad teaching, like they need to learn how to sit through a lecture and take notes, and it's almost like it sort of justifies some of the teaching methods that are being used that don't necessarily align with best learning practices. And one of the challenges here is that when we look to the literature, it turns out that that's not really the professors who've been studied. That's not really what they want. So it feels a little bit like a myth. But I think teachers get reinforcement when their students go off to college and are successful, and they come back and say, your class helped me prepare for college, right? So I think their lived experience kind of feeds into that preparation ethic. So we've seen that professional development can really improve chemistry education. We've learned that teachers might not be aware of this 3 levels of thinking, and once they're made aware of it, they can incorporate it into their teaching. And it shouldn't be a surprise that they might lack skill with the particular level because so much of their learning had the symbolic level overemphasized. So some works that are listed here help us see that inquiry along with dynamic visualization really helps student learning. And we also know from the Target Inquiry Project that Debbie Harrington and I have led over the years that the chemistry education research literature actually aids in teacher learning related to these 3 levels of representation. So PD, might be a solution for us. And we also have seen some signals from the high school chemistry teaching world that teachers might be ready for this. They might be ready for this reform around visualization. There's been a much bigger emphasis on the particulate level modeling and generating explanations, promoted not only by NGSS, but also by larger curricular reform and teaching reform projects like Target Inquiry. The redesigned advanced placement curriculum and the College Board drives a lot of things that happen in secondary sciences. And then also there's been a lot of uptake from, there used to be, well, they still exist, but they kind of started it. The physics teachers led by Hessness at ASU, the modeling curriculum. And now there is a group of chemistry modelers associated with the American Modeling Teachers Association, where the whole course is framed around models. So I think it's the right time. Is kind of what we convinced the NSF panel, that it was the right time. And so to take all what we know now and translate this into something that can support improves teacher and student learning. Our theories of change and action are listed here. And our theory of change in black, the little black sphere, is tied to some important work generated by Sherry Sutherland and others around pedagogical discontentment. And so the idea here is that if we can help teachers see the gap between how they're teaching and how they might want to teach, right, more aligned with reforms, that if they can understand that gap, then that serves as a motivator. And so that's how we're framing the teacher change. So we're trying to almost stimulate that discontentment. So it motivates them to look at other ways to support student learning. And then as far as the students go, we're using that very reliable conceptual change model. We want students to have scientifically accurate ideas about what's going on and why it's happening in terms of chemical reactions. And so we need students to confront their inaccurate ideas in the instruction. And then lastly, and you probably shouldn't be surprised about this, but this idea about levels, right? So some important work from David Tregust comes from this notion that, the relations between the different representation levels are also important understanding relations. And we need to make sure that those relations are considered in this idea of we have description at one end of the continuum and we have explanation at the other, and the extent to which those representations support that sense making on the description side. Kind of how do you translate that to help people be doing that in the explanatory sense? And so those relations of representation levels and description and explanatory levels becomes important. So those ideas help us think about how we can help student ideas change and teachers' ideas change. But mechanistically, how are we going to do this, right? So we're going to do this through professional development for the teachers on the VisChem approach. And the VisChem approach I mentioned came from work from Roy Tasker. And so I'll tell you a little bit about the VisChem approach here. And so what we have here is it's very much framed around a cognitive learning model that stems from information processing theory. And you can see across the top that arrow there, perceiving, selecting, processing, and encoding, right? So how do, the brain, see some new information, here's some new information. It gets kind of selected through this perception filter. Then it's processed in the working memory and then encoded into either as new ideas or changed prior knowledge. And then there's that feedback loop where the prior knowledge is informing what kinds of things make it through the perception filter. And so with this particular model in mind, the VisChem approach frames experiences for students so that they can kind of methodically sort of work along with their brain during this process. And so down here you'll see, I'll just take you through. So first they engage with some kind of a demonstration. Maybe they're doing it in the lab, or maybe they're watching a video. And they're going to see some macroscopic phenomenon. And then they attempt to produce what we call a pre-storyboard. It's just because they haven't seen an animation yet. So it's pre-animation. They produce the storyboard and they make drawings of what they believe is going on the particle level. And they also use in the storyboard text because it's hard to show the dynamism and things moving around and stuff in this static drawing. And so they kind of try to describe, what is happening at the particle level. And so they're making this translation. Okay, so that's kind of what's going on here with the perception filter, because their prior knowledge is going to inform largely what kind of leaps they make, right, from the macroscopic to the particulate level. And so then they watch an animation, they watch a VisChem animation, and here it's showing this particular redox reaction. And during the watching of this animation, they don't just watch it once. The teacher guides them through it. They have peer discussion most frequently. They'll watch it probably 3 or 4 times, and the teacher might help them attend to different things. But they look for these key features that are particulate level kinds of things that are giving rise to what they're seeing at the macroscopic level. And then they go ahead and they produce again a storyboard. And this storyboard is based on the key features they've seen in the drawing. And now they're having an opportunity to revisit and hopefully reform some of their earlier ideas. Once they do this, they're starting to get into more explanatory frameworks. So it's not just what's happening. The teachers should guide the students to get at the why behind it. And then they can transfer this learning to a new context. So this is the VisChem approach, and this is kind of the basis for our PD. But we don't just do PD, right? In our group, we do research. And so the VisChem Institutes, which is the PD, and the teachers' classrooms, once the teachers are done with the institute and go and implement, those become our laboratories for addressing our research questions about teacher learning and student learning. And so the aims of the VisChem Institute, the PD, is we want to improve teacher and student conceptual understanding in chemistry. We want to improve PD models with the hope that the VisChem Institutes can become a useful model. And then we also would love to see better national and GSS alignment through this 4-day institute and then continued support afterwards. Now, here are some overarching research questions. And because the project just started about 8 months ago, I don't have answers for you. I'm so sorry. I mean, you invite me to your place and I don't bring answers. But we have started really uncovering some things related to research question 1. So I'll give you a moment just to read these so you can have a feel for what we're up to. Okay, so again, we're going to really kind of focus on teachers understanding. But we got to tell you how we got our teachers. So to recruit participants, we put out an announcement on Chem at Exchange, which is supported by the Division of Chemical Education for the American Chemical Society, and then also some existing projects that Debbie Harrington and I led, where we amassed a mailing list of about 4,000 high school chemistry teachers. That's target inquiry. And so we reached out, and we also had a website for the VisChem project, and we directed people there to learn about the project and then apply. And so this is the most insecure, I think, moment in a research project, right? You put out the call and you're like, is anybody going to come? Is anybody going to want to come? Is anybody going to want to sign up? And so we just had no idea. But the good news is that a bunch of people did. And so I'm going to walk you through our selection process. And the reason that I wanted to focus on this today is, as a researcher, I have not been in this position before where we had way more people than we needed. I actually got to do sampling as opposed to just, kind of convenient sampling and getting everybody involved, and trying to crank up that sample size as much as possible, and to make some inferences about a population. This was like legit sampling. It was a really fun and interesting thing that I wanted to share. So we went from applicants to candidates with some inclusion criteria. We went from candidates to finalists by looking at some specific features of the people in their schools and then weighting those. And then we went from finalists to participants and alternates in looking at some of their qualitative answers. So we had 166 applicants for 16 spots. So clearly the advertisements seem to work pretty well. So these 166 applicants came from 38 US states and outside the US, although we were only supporting folks inside the US. All the teachers taught between 1 and 5 chemistry sections per day. They had years of experience ranging from 0 to over 25 from the teeniest schools. Yes, high school, 29 people. okay, to schools. I've never even been to a school that's had like 3,400 students, coming from all of the National Center for Education Statistics locale types. They classified the different types of communities, and the schools served racially, ethnically, and socioeconomically diverse populations, which was great because that was a goal of our project. And we were able to, recruit uh, a lot of schools that have high populations of underserved folks in STEM. So that was really cool. So how did we go from applicants to candidates? We just started screening. They needed to teach at a U.S. school. We thought that the years of experience, we needed them to have enough so that they will have like tried out all the things they learned in student teaching, right? And we're ready to change. But not so many years of teaching that this investment in them, we wouldn't be able to reap those benefits nationally. So we found kind of a sweet spot there for years of experience. We also had some teachers who taught advanced placement or international baccalaureate or dual enrollment classes, that is high school chem classes where they get the students get college credit. And we thought that was okay as long as they were teaching some kind of like first year general chemistry. So we did all this before the pandemic, right? And then it was time to select the teachers, and that was in February and March. So we had some new criteria, and that is who wanted to come to a remotely delivered institute as opposed to 4 days in beautiful Oxford, Ohio. And so we knew that we were gonna like lose some people, right, who are interested in doing kind of a residential experience. And we had to move it online because of the pandemic. So we had 166 applicants that were down to, after this, 70 candidates. We also took a look at these free response items that they responded to on the application. So I'll give you a moment to check out what we asked our potential VisChem participants. So we had these little narratives that each of our 70 folks had given us. And so what we had hoped to learn from their answers was we wanted to get a feel for how student-centered versus teacher-centered their classroom was. We knew if they had a really teacher-centered classroom that they're probably not going to adopt these very interactive kinds of pedagogies. We also wanted to know, like, do they want to learn what we're teaching? How well aligned is our VisChem Institute goals with what they want to learn? And then also, how willing were they, and what was their ability to adopt new technology? Because the VisChem animations, are obviously a technology in and of themselves, but with COVID, it was really important that they would be willing to learn technologies to do the institute, and then also in their subsequent year of teaching, which we predicted was going to have some kind of online component. So just to do the typical week in a classroom, we did a very, very kind of course level coding. What we were trying to figure out is like who talked about students and what students did. That would give, somebody a 2 if we thought it was a very student-centered classroom. They would get a 1 if it was teacher-centered, kind of framed around lecture. They say things like, every day I would give notes. That's a thing. Giving notes is doing a lecture in high school chemistry talk. But if they gave us like a superficial description, if they said, we meet 5 days a week and I teach Chem 1 and, Chem 2 without any detail, then they got a 0. So this kind of helped us with that qualitative criteria. But the other piece, and maybe the larger piece that took us from candidates to finalists, we're looking at a lot of other variables, considering those and weighting those accordingly. And so you can see here in the check boxes, these are some of the things that we grabbed about the school from the National Center for Educational Statistics. And this was really important to us because we wanted to support the schools and the teachers who don't always get the stuff, right? So we wanted to focus on schools that had a higher economic need, as well as schools with a higher minority population. The other thing we wanted to focus on was we wanted to make sure that if the teacher, was teaching like 10 students versus 100 students a year, we thought we would get more efficacy out of the project meeting at schools if we pick teachers who had larger numbers of chemistry students. And so you can see here in this diagram at the left, we assigned weights to these variables. We visualized the characteristics of the top 34 applicants in that list. We examined the distribution of the characteristics, and then if we didn't think it was the right distribution, then we reassigned or modified the weights. And so we iteratively weighted these things. And what's important here is that if we were just doing a research project, I think that we might have had different priorities. But because we were doing a professional development project where we were trying to support people who are either underserved or underrepresented, that kind of shifts it. And luckily we were able to generate a list where we had a lot of diversity. I'll share that in a bit. So we ranked the candidates, we kind of came up with a cutoff score, and we ended up weighting economic need, minority serving, and number of intro chemistry students as among the highest categories, with years of teacher experience being in the middle, and then their typical week categorical coding that I showed you earlier, that ended up having a lower weight. Turns out there wasn't a lot of variability. We had mostly ones, a few twos, and a few zero. So this ended up not being as useful for us in terms of our structure. So our 70 candidates got down to 34 finalists. And we took a close look at geographic diversity. We didn't want to have one state overrepresented. And then we also looked at the answers to the other responses in the hope of getting our 34 finalists down to 24 participants. And so this qualitative coding of responses and this more holistic review after we did the weighting enabled us to select 20 participants. And I know that these are too small to read. I guess what's most important is looking at the variety here among our criteria. So you can see here we had a lot of states represented. We had diversity in teacher experience. You can see with most of our teachers, being not brand new, but also, not at the end of their career. Our school locales were diverse, ranging from large to small rural communities. We had a high percentage of schools represented by the teachers with relatively high percentages of free and reduced lunch. You can see most of our people are about 40% or higher in terms of their schools percent of free and reduced lunch, reflecting the socioeconomic status of the school. In terms of percent racial and ethnic minority, we had a lot of different kinds of school, but you could see that we had a number of schools in the 50% or higher. And then that prior molecular visualization experience, that was one of the codes. We thought that was going to turn out to be important. And we could see that most of the teachers did have a little bit of prior experience, either with physical models or computer aided models. So here are the people. So what are we going to learn from them? Well, the first thing we wanted to do was we wanted to collect some teacher and student data before the VisChem Institute. And so we were kind of thinking in this case, the teacher participants were in the role of a learner, as a learner in the PD, but they're also a teacher, that's their job. And so we used a concept inventory to identify how scientifically accurate the teachers and students' preconceptions were about the chemistry content that overlapped the VisChem Institute. So this was really fun. And I know that, SED is all in instrument design. So I thought you would think this is really fun. But we use questions that were from published instruments. And we're not, when we do like instrument design, that's like the only thing we do. So this was really hard because this was, part of what we had to do. So we identified 21 multiple choice conceptual questions that were largely particulate in terms of the chemistry level that they had, maybe translating between like particulate and macro, or particulate and symbolic, but there were a lot of particle level pictures. And we also added an I don't know response to the questions. And so for these 21 items, I've just got some kind of course level statistics here, descriptives for you. So we had 29 teachers take it because we opened this instrument up for our teachers that we selected plus the alternates because, well, we thought since it was going to be delivered remotely, there was a much higher chance of somebody bailing kind of at the last minute and not showing up. So we thought it was important to have a set of alternates on deck. And some of the alternates, 9 of them, actually took advantage of giving this instrument to their students as well as taking it themselves. And so you can see the teachers did quite well. There was a mean of 86. Okay, and then sorry about my end for the students. The students didn't answer all the items. So the students, we had a minimum of 612 students do the items. We had some items that were taken by as many as 788 students, but they were all different. So that was kind of messy to show you. But on average, they got about 25% of the items correct. Okay, so going back to that theory about pedagogical discontentment, right? The students, this was taken by students in April and May. It's the end of the academic year. These are core conceptual kinds of topics in high school chemistry. So when the teachers got an opportunity to see the data from their class, as well as the data from the aggregated, all the students who took it across the sample, it had the desired effect of recognizing that there's a lot of room to grow. The I don't know rate was kind of fun to think about. The teachers, there were 3 questions where one teacher said, I don't know. And it was the same teacher, by the way. And then the students, it was only about an 11% rate. Because, because I was thinking, well, maybe they didn't do so well because they just didn't know. Maybe because they hadn't seen these representations before, that kind of thing. But you can see it's a relatively low rate for the students rating. I don't know. So we wanted to know if there was like some kind of relationship between the items that the students did well on and the items that the teachers did well on. And so this is just a plot of the percentage of students that got it correct versus the percentage of teachers that got it correct by item. And you can see the numbers are labeled. I know the numbers don't mean much to you, but you can just see there's 21 items here. And there's this kind of interesting, kind of positive relationship. But what I was kind of curious about was like, what's going on down here? So these were items that the teachers didn't do very well with. So we took a closer look at those to see if that would inform us. And I apologize that this is fuzzy, but I wanted to share with you the way that we presented the results to the teachers. So we gave the teachers, each individual teacher got a report of the correct answer, and then the distribution of their student answers. And this item was pulled from their report. So it's a bit pixelated, but this item actually comes from an inventory that Jim Burke and I published back in 2006. Anyway, this is about phase changes, right? This is the vaporization of ammonia, okay? 62% of the teachers got this correct, and 24% of the students got it correct. So, in terms of what this means for the professional development, we're not sure yet, but what we do know is that this is, a cautionary kind of thing that we need to have on our radar as we continue to work with and support these teachers. Another item, so this one kind of surprised us, to be honest. Like we were thinking, this idea about what happens when, ammonia is vaporized, right? This idea that it decomposes into elements. We thought that might be a popular student idea, but we didn't have any idea that a number of teachers would pick like response D or response C. Actually, I don't think anyone picked C. It was response D was the popular choice for the teachers who got it wrong. Anyway, the one that didn't surprise us was this one. So this particular item kind of gets at a very popular misconception that was first published in Journal of Chemical Education by Galley. And it's this idea that bond breaking is exothermic. Obviously, that's inaccurate. And we made it into a particulate item, but the crux of the item is really, is energy absorbed or released when a bond is broken. And so this is a very, very prevalent misconception. Our group's done some subsequent work on this with college students, and the Brett's group at Miami has also done some work on this. And so the 10% students correct, that didn't really surprise us, but the 66% teacher correct was one of those things where it's like, okay, noted. We need to be paying attention to this as we move forward with the teachers' development. So some quick conclusions to this question of how scientifically accurate are the teachers and students' preconceptions about VisChem content? Well, the students grossly underperformed as compared to the teachers. We see that. Teachers held a few common misconceptions, but overall they did okay. There's room to grow, given that the students took this at the end of the academic year. And in terms of testing out that idea about a pedagogical discontentment oriented goal, the scores support that. And I don't have the data to share with you, but the teachers reflected on these and the teachers wrote about the scores, the student scores, and it was obvious that they noted a problem. I think what happens is the teachers had been asking kind of low-level descriptive kinds of questions that the students can get right, and so their belief is that the students know more than they actually do. And so giving the teachers an opportunity not just to read about it in the research literature, but to see what their students did on these items turned out to be really powerful in one of their reflections. But we haven't methodically analyzed that yet, so I can't share that with you yet, but it's coming. All right, so yeah, so this was pre-VisChem Institute. Then we did the VisChem Institute, and I'm going to tell you that planning a 4-day synchronous and asynchronous faculty development to be delivered remotely was not what I planned to do when we submitted this grant. So we spent, I don't know, it took us 6 weeks to plan the PD after it had already been planned, if that makes sense. Like we had already planned the PD for face-to-face, and translating it into a remotely delivered, student-centered kind of experience it took a lot more time than we would have thought. But the good news is we were able to do it, and I think maybe we learned some things. So the first thing we had was that the teachers engaged in VisChem as a student. And so we tried to foreground the particulate level and its connections to the macro and symbolic levels in all of these like images and visualizations that we use. So that was an important aim that was built into the Institute. We needed to help teachers recognize how the emphasis of the limitations inherent within representations is part of teaching chemistry. It's not just a VisChem thing. It's whenever you're teaching science and you're using models, people have to think about like the limitations of the model and the assumptions underlying the model. And we were able to do this with different kinds of activities, breakout activities on Zoom. And then there were some informal communications on Slack that we had set up a kind of a Slack workspace for our teachers. And so we saw some evidence of them kind of becoming more aware of the idea about limitations and how that factors into discussion. We needed to support them in facilitating this sense making, but as learners. And so again, we had to generate a whole bunch of kind of student-centered activities, and we couldn't just do like a really long Zoom meeting, a 4-day Zoom meeting. God bless, that would not be good. We collected some feedback in the middle of the Institute, and that enabled us to model the idea of making sure that your understanding of students' perceptions of their learning are indeed accurate. So we could model that for them as a good practice. And then we had to do some course correction in the middle to support their learning. So they gave us some really good instances. Um, so in modeling evidence-based teaching practices, we wanted to teach the PD framed around the same cognitive learning model that the VisChem approach is. So we started with priming the attention filter, and we did that by having the teachers read and discuss some papers on common misconceptions associated with the chemistry content that they teach. And so this literature circle became like a recurring activity in the Institute, and this enabled us to kind of get their kind of get them invested in the fact that they're kind of not alone, that there's a whole research base out there to support them, and also to start to get them thinking about their own preconceptions. We also thought about how do we reduce cognitive load in a 4-day Zoom delivered institute. So a couple things that we did was we had these tech check appointments. And so Kat and Matt met with every single teacher for 30 or 45 minutes in the 2 weeks before the Institute to help them download and install and use every single program that was going on in the Institute. And it was great because they built some fluency in some of these technologies that were brand new to them. And that way we could model some of these more student-centered things. We also had the handouts via email. We had different reading guides. We had everything was hyperlinked, everything was tied to a Canvas site, and that was more like the cognitive load of sort of being in the Institute. But within the content, you can see up here at the beginning, we tried to help them understand chunking as a cognitive activity and how they might be chunking concepts in chemistry differently because they have more expertise than their students. And so we kind of zoomed in and out of this idea about reducing cognitive load. There's cognitive load associated with the content, then there's cognitive load associated with the tasks, and then there's cognitive load associated with both. So that was a theme. And we also were trying to help facilitate the linking of new ideas to existing ideas. So recognizing that, prior knowledge is likely informing the subsequent learning that's happening. And so keeping synchronous and asynchronous activities, keeping them both there. So there were times where the teacher would go off and do something and then come back to the Zoom. Keeping those diverse. We use Poll Everywhere, Google Docs, and Google Slides. We use breakout rooms for small group discussion. And then we encourage the translation of what teachers learned as students into them developing some lesson plans. And I'm going to share some of that data in a bit. But the last thing that we focused on in the Institute was sustaining a community of practice. So we started this Slack community. We also kept the channels open, the Zoom open. So at lunch, people would like get together in breakouts for lunch, so somebody they met, oh, hey, I used to go, I went to that school. Hey, can we, meet for lunch? So we tried to facilitate all of these important kind of teacher-teacher connections that we knew were going to be easy to cultivate face-to-face, but almost impossible to cultivate in the remote environment. Another way that we tried to sustain the community of practice was we had the teachers reflect on the learning outcomes before and after the Institute. So these are too small to see, but we sent them to a Canvas page that listed the learning outcomes for the Institute, what they would learn at the Institute, and what they should be able to do when they leave. And the reflections were really important because what it did is it created this idea that they have this like professional identity that's tied to being a VisChem teacher. And then lastly, we created an online repository on a Google Drive, and then as well as YouTube with all of the teacher resources ranging from learning designs to animations to narrated animations, and everything they produced in the Institute, we uploaded to the resources and tools so that they could access some of the work that they had shared with and discussed with other teachers. Okay, take a breath. So what do we have? We have this Institute that we did, and we have some early data. So I'm totally excited because this is the first time that we've shared this data out from our team. So excited to see what people kind of conclude from this, as well as and how that matches what we're seeing. So the teacher data from the VisChem Institute is going to start with this idea of looking at them as learners and looking at their storyboards. And the sub-research question this answers is, how does the VisChem approach affect teachers' content knowledge? And we're saying content knowledge that's operationalized as the features of their drawings. So before we were looking at those answers to the conceptual questions, now we're moving to the teacher drawings. So the storyboarding process becomes more important here. So again, going back to that, they observe a macroscopic phenomenon, they draw a storyboard. Here we've got that redox reaction keeps coming up. And here we have the VisChem animation, and you can see the copper lattice, and then you can see a lot of water molecules, which is what we would have in this silver nitrate aqueous solution. And then drawing a post storyboard, that is a storyboard after they viewed the animation. So this is what the teachers did in the Institute. And so what I'm going to do is I'm going to jump to one of a whole bunch of codes that we used, and I'll tell you a little bit more about the coding process, but I want to first share with you kind of how these codes worked. And so one code is formation of silver metal. We abbreviate that FSM. And so macroscopically, they can see the silver metal kind of forming on top of the copper, and also silver on top of silver as those little trees grow. Okay. And so reflecting that in their particulate level picture is important. And when they got to view the animation, right, they could see like the hydrated silver cations, right, that would be like deposited onto the surface of the copper. So they'd see the silver metal onto the copper metal, and the silver would join the lattice. But then they'd also see silver stacking on top of silver. And so these were important things that we thought that learners should be attending to in this particular redox animation. So here's the pre-storyboard from participant number 118. And so you can see the storyboard structure is they draw the reactants before, during, and after the chemical reaction. And as well as drawing, they have the opportunity to write stuff. So we don't have time for you to read all this. So I'm just going to focus you on this explanation, and I'll read it to you. It says, copper is losing electrons while silver ions are gaining. Neutral atoms are insoluble while ions are soluble. And if you look at the picture, there seems to be an emphasis on this electron transfer, which good news, right? I mean, that's the basis of a redox reaction is electron transfer. So that's a good thing. So, there's a lot for us to attend to here. And we can even see some of the silver atoms kind of stacked on top of the copper lattice as silver is basically, getting reduced. Silver ions, that is, are being reduced. And then down here we have something that might be promising but might be troubling, and that is it's like the copper lattice goes away. And so what we worried is that, like, is there this belief that every single part of the copper lattice is going to be gone, because it turns out that the silver is going to coat the copper lattice, and all the copper ions, or excuse me, copper atoms are going to have access to the solution or to react with the solution. So we're like, uh-oh, do they think that every single copper metal atom is replaced by a silver? We didn't know. When we look at the post storyboard, we see some evidence of silver stacking on top of silver. So this would be present. Then we would say that the FSM code was present here. And so that is, I don't know, kind of good, right? Because we see that they attended to that in their post storyboard. Now, this code list, it's a lot to read, but this came from Roy Tasker's work. And what's important about this is it gives us a deductive set of codes that we can go through and look at the storyboards and look for these different criteria. We simplified these 11 down to 10. And then our goal was to try and figure out, how does the VisChem approach affect the teacher's content knowledge? Let's look at their drawings. Now, we were a little bit short because we had some important phenomena that wasn't associated with those codes. So we added 3 codes to their storyboard that is just showing solid sodium chloride, atoms vibrating in the lattice, that there's a size difference in the ions of sodium and of chloride, and there's also atoms are in close proximity. So those more specific things were added when we analyzed the teacher's solid NaCl storyboards. Now, the next storyboard that they did was the dissolution of NaCl. So NaCl being dissolved in water, and 2 codes that needed to be added there was the competition of water molecules as well as the transient interactions between the solvated ions. So as chemistry experts, in using these animations, right, we were able to add these codes. And then the last storyboard is the one that you've already seen a little bit of, which is associated with this redox reaction between copper metal and silver nitrate solution. And here we have formation of silver metal, there's that FSM, lattice of copper metal, and then the exchange of electrons. Okay, so when we put all this together, we could look at the teacher's storyboards and say which codes are there. In other words, which drawing features are showing up? What are they attending to? So this big long list of codes is not as important as the fact that when we looked at the solid NaCl, all of these codes did not apply. So we didn't set that as the standard, okay? So if they did this with a high level of fidelity, they would have a total of 4 codes for the first storyboard, 13 codes for the second, and then 17 codes for the Redox storyboard. So as the conceptual complexity of what's going on increased, so did the features of the particulate animations and drawings. So these numbers are kind of not super important, but what's important is just that they're increasing as we move from storyboard 1 to 2 to 3. And then we got slapped by some really significant limitations as we were doing this work. The first one was this realization that some codes are fundamentally difficult to draw. So even though we had drawings and explanations, there were certain really dynamic things going on in these animations that were super hard to represent. So we thought, well, are they drawing them? Are they trying to draw them? Are they just blowing them off? Because like, how do you show competition between water molecules, right, in a drawing? And so we knew this was a limitation of what this capture was of these teachers' ideas. And that led us to worry that the storyboards might not be strong, not enable us to make strong claims about teachers' chemistry understanding. You see, what if they thought about something but didn't draw it? What if they attended to something and deprioritized it, right, and didn't draw it? And so we were kind of stuck because we thought the analysis focuses on what they attended to and drew. And how we saw that change from pre to post storyboard. But can we make claims about knowledge from this? And we're still really on the fence. We're very concerned about going that far. But it's early, so I can share with you kind of where we are. So summarizing the storyboards here, what this is showing you is this is across all the 20 teachers that for the pre-storyboards, they had 71% of the codes that they should have. And for the post, they had 91%. So this is across all teachers just for that very first simple one. And just a reminder to you, there were 4 codes associated with the solid NaCl. So 4 codes times 19 participants. So the denominator of this fraction is 76. So that's where the 91% comes from. Okay, just wanted you to understand the percentages because we're just looking at NaCl across all teachers. And so when you look at the score, you're like 71%, 91. Hey, that's pretty good. But then when we move to the more complex content and storyboards, we're starting at a very low percentage and it's not going up much as we move to post. So this is an important realization here. It turns out for this second one, and just to point out, we had 20 teachers, but for some reason, one of our teachers, well, she was sick and she didn't do all the storyboards. So that's why we have 19 participants listed for some of these analyses. Sorry about that. But we had a total of 247 codes for that, and then 323 codes. Again, 17 codes times 19 participants. And that's what is reflected here. So this is kind of slicing and dicing across, by task. Okay, so this is all the teachers task by task. It's useful for us to think about this sliced a different way, which is if we combine all 3 tasks and look at a profile of the teachers and we summarize their performance. And it turns out that we had a total of 5 teachers have, and by the way, these numbers here these cutoffs are a bit arbitrary. We just kind of looked for where there was a bit of a difference, right, in terms of just inspecting to see how we can categorize these. These were not done by any kind of analysis. It was just inspection. So what we did is we saw that 5 of the teachers had included features in the storyboard. That is, they had more than 72% of the codes. And then at the low end, we also had 5 teachers who had fewer than 50% of the codes, and then 10 of the 20 teachers were in between. Now, just a reminder here, since we had one teacher who didn't do all the storyboards, okay, there's one teacher here whose total only comes from from one of the 3 storyboards. But nevertheless, we can see that there is definitely variability in the teacher's use of these particular features to describe the phenomenon for each of the 3 storyboards. Now, another way to slice and dice this would be to look at it by code. And so here what we have is, I'll kind of walk you through what the zeros and ones mean. Zero means that the feature was absent. It was coded as absent. One means it was present. And what we were really interested in is this change from pre to post. So I'm going to direct your attention here to the second row. So 0 to 1, this means that it was not in the pre, but the code appeared in the post. And here are the four codes right here. And just a reminder that AVL stands for atoms vibrating in the lattice, which is a really important feature of solid materials. And so it was kind of cool to see that 63% of the teachers went from not having it in the pre to having that in their post. So that's good news. Okay, so that's just showing how many participants went from 0 to 1. Okay, if we blow this up and we look at this across all three of the storyboards, which I'll share here, and again, remember those codes increased as did the complexity of the animation. What we find is that there are a number of codes that are absent and stay absent. A good way to show that is here. We've got more participants did not include this code in their post storyboard. So everything that's got this little peach color, okay, means that more participants did not include it in their storyboards. The blue is better news. More participants included it in their post storyboards, but these percentages are relatively low. This NWM one stands for number of water molecules. So in the dissolution storyboard, post storyboard, 58% of the teachers attended to showing those hydrated ions and attending to the number of water molecules around them. So what does this mean for us? Well, in terms of how the VisChem approach affects teachers' content knowledge, again, operationalized as drawing features, we saw that many teachers attended to these atoms vibrating and the number of water molecules, but not necessarily in their post, okay? The teachers ignored competition of water molecules and transient interactions between solvated ions. And what's interesting about those is they're both very dynamic features. So more than 74% of the teachers ignored those. So our conclusion at this time is that the teachers either overlooked these codes or features, or they simply didn't prioritize them for their drawing. But we don't know which. So what we do know is that this can inform our professional development. We want to introduce this coding scheme earlier in the VisChem Institute so we can encourage deliberate attention to the features of the animations and taking that next step of representing those features in the storyboards. And so although our research conclusions are on the light side for this particular analysis so far, we have found something that's going to support the continuous improvement of our PD. Okay, the last thing I want to share with you, this is the very last thing, is the VisChem learning designs that the teachers generated for precipitation. That is, how do the teachers' learning designs, and when I say learning designs, I just mean their lesson plans using VisChem, how do their lesson plans incorporate pedagogical features that are central to VisChem? Okay, so we did some inductive coding with, now we're thinking about the teacher in a teacher role as opposed to in a learner role. And we see out of the 20 teachers, all had pre-storyboards and viewing the VisChem animations in their lesson plans. But 18 of the teachers had drawing post-storyboards. So this is an important part of the VisChem approach that 2 teachers left out. In coding the other features of their lessons, this was a lesson on precipitation, we saw that 17 out of the 20 teachers attended to reducing the cognitive load for students, and these yellow codes show you the way in which they did that. So they had the video going multiple times, no narration to having narration, drawing attention to pieces, asking questions for students to have to answer during the animation. And so we can see that they really, this was a really positive finding that they latched on to this piece because the animations are quite complex. And so this little legend kind of lights up those colors I was showing you before. So yellow means, blue means more than 10. And then pink means fewer than 5. And so kind of thinking about this progression here of activities, the pre, the viewing, and then the post storyboarding, there were some interesting things that we observed in those lessons. One was that 16 of the 20 connected to the macroscopic level. Okay. They also, we had some that were connecting or comparing their pre-storyboard to the animation. We also saw some really important things tied to discourse, and that is that they were creating space for student discussion, and then the connection to the macroscopic level happened at the beginning, but then it also happened here for some. So this 16 out of 20 and this 9 out of 20, we had some overlap. So almost all of the teachers made this connection. And then here in the pink, we had a few other things that we were able to see tying to this student discussion, like reaching consensus, valuing peer feedback, and building that into the lesson, as well as having the students go through a deliberate compare-contrast. And then lastly, drawing post storyboards, we saw a number of the lessons had storyboards as a follow-up assessment, had students connecting the chemical reaction in the animation to a new reaction or a new context, and then connecting the symbolic level. So the symbolic level was somewhat de-emphasized in this particular lesson, it seems. And then, here are some less frequent things that we saw at the end of the lesson, like student discussion, and then having learners do some comparisons. And so this gives us some really interesting insights, and there's definitely more to come with this, because we know now of how they're thinking about VisChem as a teacher rather than just as being a learner. And so some conclusions for research and for PD from this particular question in looking at their learning designs was almost all the teachers prompted students to make macroscopic particulate connections. And some teachers made some symbolic connections. We also learned that the teachers created a space for discourse and that there was a lot of variation in the detail and the logistics of the lessons. You're probably not surprised that some teachers produced very detailed descriptions while other people had things that I would characterize as skeletal at best. But the big finding, I think, here is number 5, and that is we see some early evidence of a hierarchy of pedagogical reasoning that might be associated with these 3 levels of representation in chemistry, and we want to explore that further. In other words, if people are just for the first time learning about these 3 levels of reasoning, we wouldn't expect them to be making as large of pedagogical leaps in their learning about the VisChem approach. And then lastly, we think these codes that were generated about their lessons will be helpful to us. And so what we're going to do is we're going to introduce those codes after the teachers draft their first learning design, and we're going to help them to revise their learning designs. They did this before in the Institute, but it was just peer evaluation without any sort of guidance or rubric. But we think these codes are going to help support that peer revision in hopes that they'll say, hey, when am I having the students discuss things, or am I having the students think about this on all 3 representational levels? So some cues and some criteria for maybe some good learning designs. We think that we can beef that up in our institute and support that. And so to wrap us up, some big overarching implications for professional development, teaching, and research, and of course, future work, because, we're just getting started. The extent to which teacher conceptual understanding is evidenced in storyboards needs further exploration. We are not sure what claims we can make about conceptual understanding from their storyboards, as you could see so far. But what we do know is that teachers' fluency with the 3 levels varies greatly and seems to affect their pedagogical learning outcomes related to the implementation of the approach. And once we start collecting data out in the classrooms, we're going to be able to beef up this idea. And I think we'll be able to collect data that might be able to help us better understand the ways in which their knowledge of the levels is affecting their pedagogical learning. And not only should this variability and fluency with levels be addressed, but it should be a factor in our data analysis and our claims making. So this particular idea about their variability with fluency in the levels, it affects the PD, but then it affects the research in terms of our interpretations. And then we're certainly looking for some potential links between the artifacts I shared with you some codes about today. Like, do their storyboards as learners in the VisChem Institute have any relationship with their learning designs that they've developed as teachers? And so that's some important future work. And then the big stuff, right? The student and teacher level data collection that happens out in their classrooms, that helps us, that will help us address the balance of the project's research questions about what kinds of teacher moves constrain and afford teacher learning when using the VisChem approach. So that's the plan. Okay, I have to thank you because you sat so nicely and just listened to me drone on and on at my screen. So that was really cool of you. So thank you so much. And I also want to say a big thanks to Roy and to Amelia. And of course, a big shout out to Kat and Matt, who do the heavy lifting. Okay, and I get to go out and present their really great work. So I'm super proud of them and excited to be here. And that's all.
Wow.
How are you, Phil? Good to see you.
Ah,
Oh my gosh,
yeah.
and now I'm breathing and I have more caffeine, so that'll help me get through the next
good.
presentation, right? Okay. Do you want me to unshare my screen for discussion? Would that be helpful? Or what do you guys traditionally do?
I think I.
Yeah, go ahead.
It's Jen.
I think if you can unshare your screen, it would be easier.
Be happy to do. Then we can all see each other.
Yes.
Hi, did everybody
Hi.
endure? Did we laugh? Everyone, let's take one of those stretch breaks or something. Oh my gosh. I feel bad. I'm imposing a ton of Zoom fatigue on my colleagues today. I'm so sorry. You guys are awesome. Thank you.
Wow.
Okay. So wow. So yeah, so the thing that's fun about this is we're just getting started. And so the excitement of sort of putting some stuff out there, you know, and hearing from trusted colleagues is just a blast. So I'm excited to hear questions and reactions and whatever you have. I think it's awesome.
Can I go?
Absolutely. Hi.
Hi, thank you, Ellen. That was really great. What a great project, and so impressed by how you've been able to adapt so quickly to the new times.
That's so kind of you, because it doesn't feel that good right now. So thank you.
Yeah. So one question that I have, something that we run into a lot when we're trying to work in socioeconomically diverse school districts, a lot of the teachers will tell us, well, our computing resources are really not that great. So how are you going to manage that with your teachers?
Yeah. So remember how I mentioned those tech checks that we're doing?
Yeah. Yeah, I was curious. So
yeah.
I thought that's really great.
So what happened was, okay, so before, okay, we're all friends, right? So I'm just going to tell you like the real deal. Okay. This, after getting a few $1 million grants, you know, I was like, oh,
Ellen, do you want me to stop recording?
Oh, sure. Whatever you want. Yeah, probably. No, I don't care. I think it's good for people to hear this. You know, what happened was we, you know, after getting a few $1 million grants for like the target inquiry project, you know, like we generated this idea about the VisChem project and we submitted it and it didn't get funded. Has that happened to anyone on this call? I think you're also successful. No, Phil's always gets funding.
No,
Phil,
no, that's not true.
Phil wakes up in the morning and gets funding. But the thing is that Gerhard's like, I do too. But the thing is so we revise and submit the second time. No. Third time. No. The fourth time was special. And the reason the fourth time was special is if it didn't get funded, I was going to become a real estate agent. Okay. Anyway, I know I could sell it. Don't you think? I watched all the Love It or List It shows. But anyway, so here's what's important to answer to your question. Between submission 3 and 4, we collected some data from teachers who we already had a relationship with around the technology. Okay. And we learned some important lessons, which is a lot of the things that like they couldn't access the VisChem animations the way that they were set up because they had Chromebooks, and Chromebooks can't have video files, right?
Mhm.
So that's why we had to do the YouTube. So all the videos had to get converted into YouTube videos and stuff. So that little between year 3 and 4, and you can see I'm not a real estate agent, so we had success in year 4. But the lesson to everybody there is persist, right? Especially to, like, I'm thinking of Chen, who is a relatively new investigator. Chen, you can't give up. Okay, don't give up. When you get discouraged, you just have to have a really stiff cocktail and keep going. Okay. But
No.
anyway, he's like duly noted. Okay. But anyway, so that helped us. Number 1. Number 2, the tech checks, we learned some things. We learned about bandwidth issues. We learned about problems with like students who couldn't access anything at home. So their homework assignments had to be built around things that didn't involve the animations. Okay. They had to have something that they could basically download onto their computer or like a Google Doc. So we got very Googleized in the time from when we had to like conceptualize the project to start the project. Everything got very Googleified because of the prevalence of Chromebooks. And then the other thing that happened was we had some classrooms where not every student had a computer. And so then it became with, all right, so how do you do a student-centered lesson when the animation can only be shown by the teacher at the front of the room? So that was another constraint. Yeah. And so that's where in the VisChem learning designs that the teachers produce, we would see things where the teachers would show just a part of the animation, and then they would discuss in small groups a particular question. And so the pedagogical adjustments that we kind of planned to support the teachers with, some of the teachers kind of automatically did that, and then they shared it with others. And for some reason, it has a lot more street cred when it comes from another chemistry teacher than when it comes from me and Roy. So anyway, but yeah, so we're like living with those limitations. And what's cool about it is that we haven't come across a classroom that didn't have one computer in our sample. Now, that doesn't mean that there aren't schools out there like that.
Right.
But of the people who applied and who were selected, we hadn't run into that. I hope that answers your question. Is that
Yeah, that's super helpful. Thank you.
okay? Thanks.
So can I ask a question to kind of piggyback on that? Is that, yes, you're absolutely right. So many schools sign on to, crates of Chromebooks, and they give a Chromebook to every kid and every teacher. And that does, as you said, have extreme limitations to them. But the other thing that I'm sure you are aware of being in Southern Ohio is the rural access issue when it comes to internet, et cetera, or, consistency of access, et cetera. So I wonder if you are able to now convert this to, I don't want to use the word canned, but something that can be accessed and gone through as a process and lessons and learning, both with teachers and with students, so that they don't have to have internet access or connectivity or et cetera, to be able to get past those kinds of access issues and intermittent internet, et cetera. So I didn't know if you had plans to put this in a format where it can be used and all of the features of it can be used, but you don't have to have the internet access.
Yeah. So what we have is we have kind of it's like a dual setup. So we've got a Google Drive with the animations, and they can download those. So those they can live on whatever place they want them to live, freely accessible. And then we have them on YouTube. So that's how we're dealing with that kind of access issue. But in terms of thinking about this as a canned thing, the diversity in the teachers' learning designs demonstrates that if we give them something that's too canned and too structured, they're not going to use it. They need to be able to like take something that they can customize and adapt to what they're doing, for them to use it. And I know that there are in science education, there's lots of different like camps on this. Like there's some people who believe teachers can't develop curriculum and they shouldn't. And so I'm not in that camp, because it's like, well, you know, they tweak everything anyway, you know, so if you can't beat them, join them, right? So I think that from the Target Inquiry Project and now in this project, we hold the belief that we're trying to teach them larger kind of strategies and the principles that underlie those strategies, so that they can adapt and implement with fidelity, even if it looks a little bit different from the teacher that they just, you know, co-planned a lesson with. And so I think the canning piece could give up some of that flexibility that the teachers tend to value. But that's a lever, you know, that like,
Right.
I guess I don't have a really good answer, because I think this is really difficult, right? Trying to decide how much needs to be prescriptive, right? And how much needs to be flexible.
Yeah.
And so, yeah, so we're starting with sort of principles and tools and keeping it pretty flexible at this time.
I guess maybe canned was not the right word. I was thinking
that's
more of a template that that they could, you know, use, but then, as you say, veer from and modify, et cetera.
Yeah,
so
so thinking about templates is actually really important. Like the storyboard, those pages that we kept showing, they look the same, and it's because we're like, here, use this as a storyboard template, you know. And what's interesting is not all the teachers did. Some of the teachers said, I don't like that storyboard template. I want to make my own storyboard template. And we're like, knock yourself out. As long as it has a box for particular level drawings and lines to draw stuff, we don't care what it looks like, you know. So it's just, there's just that lever. I feel it all the time. So thanks for identifying that, Cynthia. What's up? Let's ask Phil.
Yeah, well, no, I have some comments to make. This is really interesting, but you're in the thick of it. I mean, don't feel bad that you don't have all of these. You haven't reduced your data and have all these really firm conclusions about how things should change. I mean, you're in the middle of it, and it's going to be several years after the project is over. Just ask Gerhard and Chen.
Yeah.
Several years after the project is over, that it's all going to crystallize.
And then I'll sell you a house after that.
Well, no, I had a comment about that. I don't think you would succeed in real estate, and it's because you obviously have a preference for as many doors in a room as possible, and that's not what most people want. Like things like windows or blank walls.
Just
they don't
doors.
Want doors everywhere.
Yeah,
So
well, this is a good observation, and you know, and I'm glad that the vocational training is also, like, you guys do it all at Harvard. I'm so impressed. I mean, there's vocational counseling. It's amazing. Thank you. I appreciate it. No, but this idea about persistence, I think this is one thing that I don't think we talk to new investigators enough about. Like we say, you know, it's like they see somebody who. Like we advertise when we get the grant, but we don't usually, like I don't put on my website, hey, everybody, I failed again this year. You know, like we don't advertise that stuff. And so we need to use these kind of opportunities to have frank conversations about what it's really like out there, and then what it takes to, you know, to keep succeeding. Like it's not easy. And like I said, I really did think about, like, maybe I'm not good at research anymore. Like, why am I unable to sell these ideas to reviewers? And what's interesting is I figured out why the proposals didn't do as well. And it's good. You know, I learned an important lesson. And that is that if you get into your disciplinary, narrow text speak, then only that one panelist understands what the heck you're talking about. You know, so and I think that the more I learned in my narrow area, the better I got at that. And so, you know, communicating to a broader audience becomes a really important thing. And that's not a value for manuscripts, but it sure as heck is for grant proposals. So, you know, so really good lessons, and my grad students and postdocs are learning along with me, and it's all good.
Well, serving on panels, you realize that that panelists can not all of them get what's going on in the proposal, and
That's true.
And so you're not just speaking to your closest colleague; you're speaking to people who are very knowledgeable in their area, but may have no way to connect to the things that you're writing. So
yeah. And I think your group has really, kind of perfected that strategy. So it's of benefit to, to continue to share that with the members of the posse and, and keep everybody developing those skills. Because I think that in a vacuum, it's really hard to do that.
Yeah, but also it's, for me, I think one of the things that I brought to this process is the sales mentality. Having been in sales and having trained people in sales, it's like people who are in sales are oblivious to failure. They're oblivious. They measure their success only by their successes. It's like the number of successes, the number of failures. There's no denominator. It's just the numerator. It's like the number.
What brilliant advice! What brilliant advice for academics, because we're so busy feeling like imposters, right? We don't think about what we're leaving out of what we should be leaving out of the denominator. That is. So
Yeah.
Great advice, Phil. Everybody on the call, everyone listen. Great advice.
Okay. Well, now I have a few things to say about the VisChem PD, which
Sure.
is in working with chemistry teachers, especially, they seem to, when I've had student teachers who are in chemistry, they don't discriminate between models and truth. So it's like, I'm going to teach what's true, and what's true is, the quantum model, the electron cloud model. And when this would come up with my students, I'd say, so the model that you're trying to teach is the true one? And they'd say, yeah. And I'd say, well, what about relativistic corrections? Do you include that in the model too? And they'd say, well, no. It's like, well, it's just a model. And so what you're talking about is paying attention to aspects of the model. The models are always simplifications, and they're not nature.
Right.
So by having all these, by having essentially a rubric for evaluating your storyboards, you're saying, what should you pay attention to in each of these models? And one model does not fit everything, because you have certain kinds of chemical processes that are different from other kinds. And so,
and oxygen atoms aren't red.
Well, they are in space.
Red.
All the red glow is oxygen. Yeah.
But and hydrogen atoms,
when you draw them, you don't have to draw them as red.
Yeah. So I think it's there are some weaknesses in college chemistry teaching and learning that I think accumulate and show up in the situations that you're talking about, Phil. And it's the idea where we're not teaching science from a perspective of like what science is, right? So the nature of science is almost stripped from the chemistry discussion and instruction, and it's a huge detriment to our pre-service teachers, I think, for the very reasons you're sharing. And so I never want to like dump on anybody, but we have some serious room to grow in our undergraduate chemistry programs, because I hear professors use words like truth, and it's like, well, hold on a second, is this a philosophy class? Because scientists don't really look at the construct of truth as a thing. We're more focused on evidence and prediction and description and explanation, and that's what we do, and so people who are embedded and immersed in doing science sometimes don't know enough about the nature of science. So when they talk about their process, they're missing the things that, like, say, philosophers of science tend to address, and science education people tend to address. So,
it's not really needed to be a great scientist. You don't have to know a lot of philosophy. No, but some do. So, like Einstein was steeped in philosophy, but lots of people are not.
Yeah. So. And so I think that, using the T word in a chemistry class, it's like, that can have some damaging effects, I think, on people's, epistemological assumptions about doing science. So that worries me. I don't have an answer for you, Phil, but I'm worried too with you.
Yeah, and it's I'm teaching this course now, The Great Experiments, and I was late because the students were presenting their projects on the last day of class. So one of them did a project on, we looked at Lavoisier's experiment with mercury
oxide, mercuric
oxide. Mercury oxide, yeah, what he called calx, I guess. Yeah, and like the discovery of gases, different gases in the atmosphere, moving from the 4 elements of the Greeks, where air or wind or is a element, to, well, they're sort of different. They're different constituents of air, and there's oxygen, carbon dioxide, and all these things that we're discovering. And one of the students decided to sort of investigate carbon dioxide, and how is it different than air? And it's like, these are great stories. I mean, that's impressive science, where you take something that everyone sort of accepts, and then you investigate and find out what people believe is not true, that air is a mixture of all these different gases. And so I think a lot of that is missing in our rush to teach about, to have chemical equations and to teach all this latest ideas. People miss out on what the sort of paradigm shifts are, what the philosophical shifts are. So that is a shame.
The historical context, I think, is lost in a lot of things.
I mean, for some students love it, and some don't. But I think the stories are far more accessible than the abstractions. Yeah. And so I like the storyboards. I don't know if you realize that storyboards essentially came from Walt Disney. He did lots of storyboards when he was doing his planning of cartoons.
I had seen that Tom Hanks movie. It was Tom Hanks and Emma Thompson.
Oh yeah.
And that's the only Disney exposure to storyboarding that I've seen. But I should read more about that.
But so we've done storyboarding. I remember, and certainly Cindy remembers this. Where's my storyboard here? Is that it? Yeah. No. Is this it? No. Wait a second. Wait a second. Let's get a storyboard here.
While you're pulling that up, I'm gonna.
Here it is.
I'm gonna let the cat in.
Okay.
The cat's trying to get in, which is awkward Zoom moments during seminars. Here we go.
So we had engineering competitions, and one of the things we always had students do was they would make storyboards. Let's see, we got one at the end here. So this is a student storyboard on building a solar house that was sort of immune to high temperatures. How do you do it? And the student started with one design, tested these designs incrementally until they came up with something they think works best. And they tried to represent the features in their storyboard. And I think that this was a real interesting and permanent way to keep a record that we could later evaluate.
Well, and I think also too, the relationship between like the text and the pictures is really important. It's like the picture doesn't tell the whole story.
Yes.
There's certain things that are too hard to represent in the student's plan, right? So, I think that in early implementations of the VisChem approach in Roy's early work, right? Students might have been a little hesitant to do the words, but I think you can encourage that more, and he did, and it's turning out to be a really important part of our analysis because there's a lot of chemical ideas embedded in those sentences.
And so, to what extent do you have, as part of the professional development, have the teachers evaluate each other's storyboards or evaluate student storyboards?
Yeah, so we had one activity where we gave them 4 student storyboards, but they really weren't student storyboards. We made them, okay? And the goal was to make sure that one that looked really good and attended to a lot of the features didn't attend to all of them, and some of the features that were important in that one, in the opposite one, you know, or the second one. So we use kind of Dan Schwartz's idea of like contrasting cases that people can do more sense making when they do a compare contrast versus just giving them one thing to describe. So we came up with these two pairs of storyboards, and it was really useful. The one thing that I think we can do better in our next iteration is to do that activity twice. And the first time, you know, what do you see? And what are the differences? What are the similarities? But the second time, give them that set of 17 codes and say, now identify which of these are attended to in each of the storyboards. So we're giving them a little bit more direction and framework for thinking about storyboarding features. This is a place where I think we left it a little maybe too open.
Yeah, and you can do that if you have like 4 storyboards. You can have people rank them. And then the ranking will change once they learn some tools to evaluate them.
Yeah. I think that if we add one more layer to it, it's going to be even more effective. It went well. You know, we kind of got some desired outcomes, but then when we see it come out in the wash, you know, at the end of the PD in the teacher storyboards, that's when we're like, we need to tweak this one piece. So
yeah,
and it's like. Now.
Yeah, I know about that, the misconception around the dissolution of molecules, or whatever you would call it, where all the atoms split apart when the thing evaporates, when it turns to gas. It's like, and the original stuff there was just water, boiling water.
That's right, yeah, Osborne and Cosgrove, great paper. Yeah. I mean, and that's, you know, before, that was published before my postdoc was born. So what do you think of that there? Cool.
Yeah, okay, I get that. And it happens more and more to me.
Pretty good stuff.
Then I would personally attend to the colorblindness issue in your. Yes. I mean, you have these very light pastels of things that I cannot see.
I will make sure we do that for the next presentation. Thank you.
Well, you'll lose 5% of your male viewers.
Well, we want to keep everybody in the mix. So thanks for that. Appreciate it. Is if the storyboard is a representation of somebody's knowledge, right? And there's some other sort of filter cutting off what they're able to represent, you know, then how good can our claims be about their knowledge state around that particular phenomenon? So that's something that, you know, it's, I mean, the hard things are the most interesting. So we'll find a way through, whether it means, you know, kind of not being able to make claims in that area, or maybe it's just a reliance on a lot of different kinds of data that'll triangulate a finding related to teachers' conceptual understanding, because we're going to be seeing them in action, you know, teaching this way. I think that's going to be really informative in terms of, you know, what kinds of conceptions are more and less accurate we'll be able to see. And so if we put that together, like if we take the test and the storyboards